Jai Hind to all. Myself Dr. Uma Sharma, Assistant Professor in EC Department of Akgec Engineering College. Today, in the lecture series of Integrated Circuit Design, I'll discuss the designing of band pass filter. Basically, this topic is very important in the point of view from the exam, university exam. So, definitely from this topic, you will get one questions in your university exam. So, let's start. So, basically a band pass filter, a frequency selector, it allows one particular band of frequency to pass while attenuate the other frequency band. So, basically the pass band is between two cutoff frequencies, and these cutoff frequencies are known as higher cutoff frequency and lower cutoff frequency. That means the filter will pass the frequencies which lies between FH and FL and attenuate other frequencies which are outside this band. Okay, so from this diagram you can see that this is the frequency response and this is the pass band, which shows the filter will pass all the frequencies which lie under this band. So, FL to FH, and the stop band means the filter which attenuate or will discard all the frequencies under the stop band, whether it is low or high. So, there are two stop band in band pass filter. That's why this is known as band pass. A particular band is passed. Here in this frequency response, let's understand what are the parameters at the y-axis. This is gain, which is known as VO by V in and can be represented at AFT. That is, AF is the filter gain and this is the total gain of the filter. This 0.707 of AFT is basically the gain which is 3 dB down from this AFT. So, basically this gap is 3 dB. So, at FL and FH, gain is not AFT. Basically, the gain is equals to 3 dB down AFT. So, at the FL, the gain is 0.707. Basically, when we convert 3 dB into normal unit, then we will get 0.707. So, here the gain is 0.707 of AFT at FH and FL. And the difference between FH and FL is known as bandwidth of the filter. So, this specifies the bandwidth of that particular filter. And FC is known as the center frequency or cutoff frequency of the filter. So, from the frequency response, we have seen that at the center, the frequency is known as cutoff frequency or center frequency, and at this frequency the gain is maximum, which is denoted as AFT, total passband gain, and the gain at FL and FH is represented as 0.707 of AFT, that is 3 dB down from the highest gain or the total gain. So, now let us see what are the various type of band pass filter. So, band pass filter, depending on the particular band of frequency, we can classify into two categories. One is known as wide band pass filter and another is known as narrow band pass filter. So, how to categorize into wide and narrow? So, as the name suggests, whenever the bandwidth is very high, passband width is very high, then the filter is known as wide band pass filter. And definitely when the bandwidth is narrow, so the filter is known as narrow band pass filter. Like from this diagram, you can see that wide and narrow. Here the bandwidth is large, and from the diagram you can see that here bandwidth is narrow. So, that this filter is known as narrow band pass filter and this filter is known as wide band pass filter. The another parameter by which you can classify the filter or you can identify whether it is wide band pass or narrow band pass is the quality factor Q. This is the quality factor. Basically, the quality factor of any filter define its selectivity. How selective is the filter? So, whenever the selectivity is less, that means the filter is less selective. That means that will pass almost all the frequencies. So, bandwidth is high. So, whenever the selectivity is low or quality factor is less than 10, then filter is categorized into the category of wideband pass filter. And whenever selectivity is very high, highly selective, like bandwidth is greater than 10, like 20, 100, 200, so that means highly selective filter. So whenever selectivity is high, that represents that bandwidth is low. So whenever quality factor is greater than 10, then the filter is known as narrow band pass filter. So this you can see from the pictorial representation or the frequency response. This shows the frequency response of band pass filter. For wide band pass filter, this is the frequency response, and for narrow band pass filter, this is the frequency response. Again, the frequency response is the curve which is drawn between total gain and the frequency. And the frequency axis, you can see that this FL and FH represent the lower cutoff frequency and higher cutoff frequency, and this center frequency C is known as the center frequency. Again, this roll off rate, here it is written minus 20 dB per decade. So what is the meaning of this minus 20 dB per decade or plus 20 dB per decade? Let's understand this. So whenever we are designing any filter, first we decide what is the order of the filter. So for first order filter, the gain increases or decreases by a constant rate which is known as 20 dB per decade. So for the first order filter, the gain roll off rate is 20 dB per decade. And if we increase the order of filter, let's say second order filter, so for second order filter, the gain roll off rate will become 40 dB per decade. Similarly, for the third order, it will be equals to 60 dB per decade, and so on. So based on the order of the filter, there will be a fixed roll off rate of that particular filter. So here in this graph, you can see that basically this wide band pass filter is the combination of high pass filter and low pass filter that already I have discussed in the previous lecture, designing of low pass and high pass filter. So you can refer that lecture. So for low pass and high pass section, if we merge both the frequency responses, then we will get a wide band pass filter response. So for low pass filter, this is the design of low pass filter that will pass all the low frequency and attenuate high frequency. And this part is basically for high pass filter. High pass filter means that will attenuate lower frequencies and pass the higher frequencies. So there is one trade-off, or we can say the one condition for the designing of wide band pass filter, that the cutoff frequency of high pass filter must be less than the cutoff frequency of low pass filter, because this is the combination of high pass filter and low pass filter. So whenever this condition satisfied, then easily we can design a wide band pass filter using the simple concept of high pass and low pass filter by adding both the filter in cascading configuration. So here, if it is first order filter, then the gain will increase by a factor of 20 dB per decade, and whenever it reaches as the cutoff frequency, the gain will become constant at equals to the AFT. And for the low pass section, the gain is constant for low frequencies, and for high frequency, the gain reduces by a rate of 20 dB per decade. Whenever it is high second order filter, then definitely it will become 40, and again this will become plus 40 dB per decade, and so on. So this is the condition for designing of high pass filter, that FH must be greater than FL. These are some other designing parameters, like we should know what is the gain of the low pass section and what is the gain of high pass section. So for low pass section, this is the frequency response equation or the gain equation, VO by Vin. So VO by Vin is the total gain, and that is equals to AFT, which is the passband gain, and that will depends on the higher cutoff frequency, that is FH. So the formula is derived as VO by Vin is equals to AF upon under root of 1 plus F upon FH whole square, where FH is the cutoff frequency, F is the frequency of input signal. Similarly, for high pass section, for high pass filter, the gain is equals to AF into AF upon FL under root 1 plus F upon FL whole square. So these are two formulas for low pass and high pass section, And to get the overall gain for the band pass filter, this is the formula, because we know that A T, like we want to calculate total gain, that will be equals to A1 into A2 into so on. So here there are two stages only. This equation represents that if we are having multiple stages, then the total gain will be equals to multiplication of each stage. So here we are having only two stages, high pass and low pass. So the overall gain of the band pass filter will be multiplication of the gain of low pass and high pass section. So in this expression you can see that this is the multiplication of low pass and high pass section. So this is how we can draw the frequency response of band pass filter by using this equation if we want to draw the frequency response. Now a few more equations which we will use while designing the band pass filter is the equation for cutoff frequency, that is Fc, and that is equals to under root of Fl into Fh. Similarly, the quality factor can be calculated as Fc upon bandwidth, where bandwidth equals to Fh minus Fl. So simply by cascading high pass filter with low pass filter, we can achieve the design of band pass filter. If high pass and low pass filter are of first order, then definitely the resultant band pass filter will be equals to first order band pass filter, and if both high pass and low pass are of second order, then the band pass filter will also equivalent to the second order band pass filter, and so on. We can design any band pass filter of any order by using simply high pass and low pass filter. But one thing you have to remember, that the order of filter for low pass and high pass must be same. So like we want to design second order, then both the filter must have second order. So now come to the designing part with some numerical problem. So this is the design of wide band pass filter, and this is the first order high pass filter design. You can see that the capacitor is connected with the input. Then this is the designing of high pass filter. Whenever the input signal is connected with the resistor, then it is known as low pass filter. So basically we have connected the output of a high pass filter to the input of low pass filter, and this overall filter design is equivalent to the first order wide band pass filter design. This is first order. So first order means there is only one RC. This is RC pair. So one RC section is connected in the filter. That means it will introduce single pole. So it is first order. Whenever we will use 2C and 2R in this design, then the filter will become second order filter. While it is non-inverting configuration, because input is applied at the positive node. At inverting node, RF and R1 is connected. This RF and R1, these components are used to provide gain to this filter. So the gain, this is the gain section. This is how we can classify. This is the frequency selective network. This is frequency selective network. And this is the RF and R1. This section is provided to provide gain. So the gain, we can achieve any gain with the help of this RF and R1, and this will provide the frequency selection. So the cutoff frequency depends on the value of R and C, and the gain depends on the value of RF and R1. So this is the designing of first order wide band pass filter. Similarly, you can design second order wide band pass filter, because in your syllabus you have to design second order filter too. So for second order filter, just you have to replace this high pass filter with the second order filter, and this low pass filter with the second order low pass filter. And the designing of low pass and high pass you can see from the previous lecture. So now let's see which type of examples or problems can come in the exam. So there is one question, design a wide band pass filter, or here it is written that a band pass filter has the lower cutoff frequency and higher cutoff frequency of 300 Hz and the 3000 Hz. Design the filter and find the bandwidth and the resonant frequency. Resonant frequency is equivalent to the center frequency. Center frequency or cutoff frequency, FC. So we have seen the formula to calculate this FC. So this FC will become 948.68 Hertz, and similarly you can calculate the bandwidth. Again, one more question may be added to this example, that calculation of quality factor Q. So Q equals to FC upon bandwidth. So by using this 948 upon 2700, so definitely the denominator is more, so this will less than 1. And we have seen that if the quality factor is less than 10, then the filter will be of wide band pass filter. So from this question, it is clear that we have to design a wide band pass filter. If this quality factor comes greater than 10, then definitely we have to design narrow band pass filter. So let's see how to design the wide band pass filter. So we have to design two sections, high pass filter and low pass filter. So first step is consider the value of C, because designing means we have to find out the value of R and C for high pass filter, the value of R dash and C dash for the low pass filter. We have to find out the value of RF and R1 for the low pass and high pass filter. Once we will get all these values, then definitely we can say the filter is designed. So definitely based on these cutoff frequencies, we have to find the value of RC, R1 and RF. So let's see, for the designing of high pass section, we have to find out FL, that is the lower cutoff frequency, and lower cutoff frequency is given as 300. So with the help of this formula, 300 equals to 1 upon 2 pi R into C, we can calculate the value of R. This we can calculate because C, we have considered that, we have assumed that C equals to 0.01 microfarad. That value, you can take any value of C which should be less than 1 microfarad. This is the designing rule. So you have to consider the value of capacitor less than 1 microfarad. So I have chosen 0.01 microfarad. So by putting the value of 0.1 microfarad over there, we can calculate the value of R. So that means we have calculated R. C we have already assumed. So in this circuit, we have calculated these two values. Now for the high pass filter, just we have to calculate RF and R1. So we will find out the value of RF and R1 in the last step, but in second part, just design the low pass section. So the designing is same, the value of C may remain same, or you can take any other value. Like for a low pass filter, you can take C equals to 0.05 microfarad, but it should be less than 1 microfarad. So for this 3000 Hertz is equals to 1 upon 2 pi R dash C dash. So C dash may be 0.01 microfarad or 0.5 microfarad, whatever is the value. For this, you can calculate R dash. So this is how you can calculate the frequency selective network of the low pass filter. So this is how we can calculate low pass filter. So now we have to design the gain section, designing of the gain section. So from the circuit, you can identify that both the filters, low pass and high pass, are designed using non-inverting amplifier configuration, because input is applied at the non-inverting node. So we know that for the non-inverting amplifier, the gain is equals to 1 plus RF by R in. So this is the formula for the gain. Now here we have to calculate this RF and Rn both. And in this question, gain is not given. If gain is not given, then you can design the equal gain filter. If gain is not given, again I am repeating, if gain is not given in the question, you can design equal gain filter. So for this you have to assume the value of R in should be less than 100 kilo ohms, any value less than 100 kilo ohm. Let's say I have assumed that 50 kilo ohm R in equals to 50 kilo ohm. So RF is equals to, you can take Rn is equals to RF, and if Rn and RF both are equal, then the filter gain will become 2 for low pass and high pass. For both the sections, the gain will become 2. So this is for when gain is not given. But if gain is given, let's say here it will be given that AF is equals to 4. Then you can write the equation for gain, that is AF equals to gain of low pass filter multiplied by gain of high pass filter. And to get this 4, you can take this combination, or you can take this combination, or you can take this combination. Whatever is the combination, for that particular combination you can calculate the gain. Let's say AF is equals to 4 and we have taken that 2 cross 2. So AF for low pass filter will become 1 plus RF by Rin, that is equals to 2. So from here this RF by Rin equals to 1, and from here I can write RF equals to Rin. So here also I have taken these values. So this is similar. If you consider Rn equals to 50, then RF will also equals to 50. But there may be the cases like gain is given 6. So you can take the combination of 2 cross 3 and so on. So this is how you can design the gain section. So ultimately for calculation of gain, we have to use the formula of non-inverting amplifier configuration, and by assuming the value of Rin less than 100 kilo ohm, we have to find out the value of RF, and whatever is the desired gain, for that particular gain we can design the gain section. So this is how the analysis is completed. That means we have calculated all the values. So the filter is designed now. This is for first order. Similarly, you can design second order filter. The process is same, but in case of second order filter, this part is different. Here there will be C1, C2, R1, R2, and generally we design equal component filter. So consider C1 equals to C2 equals to C. So the formula will remain same. Otherwise, for second order filter, the frequency FL can be written as 1 upon 2 pi under root of R1, R2, C1, C2. If we consider equal component filter, R1 equals to R2, C1 equals to C2, then this will become 1 upon 2 pi RC, which is similar to the first order filter, and similarly the FH will equals to 1 upon under root R1 dash, R2 dash, C1 dash, C2 dash, and if both all are equal, like R1 dash equals to R2 dash and C1 dash equals to C2 dash, in that case FH will become 1 upon 2 pi R dash C dash. So it is similar to the first order. So only difference in the designing part, the circuit, the procedure is same and the values will also equals to same. So this is the wide band pass filter. Now let's see the narrow band pass filter. So the circuit for narrow band pass filter is totally different. So this is the circuit for narrow band pass filter. Here I have taken one example, like design a narrow band pass filter for the center frequency of 3 kHz. Here the quality factor is given 30. So definitely that will be the narrow band pass filter, and gain is also given 20. Here assume C1 equals to C2 equals to C. So for narrow band pass filter, you have to learn these formulas R1, R2, R3. First, this is a totally different design. This is not based on high pass and low pass filter. So first of all, you have to remember the circuit, and again from this diagram you can see that there are 2 C and 2 R for the frequency selective network, and 1 R, R1 and R3 responsible for the gain. So based on these circuit, you can say it's a second order narrow band pass filter. So this is second order narrow band pass filter. So first of all, you have to remember this circuit diagram. For this circuit diagram, if we have to design a filter, that means definitely we have to calculate R1, R2, R3, C1, C2. We have to calculate these values. This is the meaning of designing. So now select the value of C1, C2 equals to C, and that is equals to 0.01 microfarad. Here I have considered is 0.01 microfarad, less than 1 microfarad. You can select any value. Q is given, FC is given, and AF is given 20. These are the formulas R1, R2 and R3. By using three formulas, by putting all these values, you can get the value of R1, R2 and R3. Just place these value on this diagram and the designing will be complete. So this is all about the designing of wide band pass filter and narrow band pass filter. I hope now you will be able to design any question related to wide band pass filter and narrow band pass filter. So thank you so much. This is for